with you all. But we have Braden Croy here from Dominion Energy Innovation Center, and he's going to really talk about alternative fuels and kind of sustainability for the future. So please welcome Braden Croy.
Good morning, everybody. How are you? Good. We want to make sure that that works. Get to nerd out with some energy for the folks for a minute here throughout the day. I'm really excited about it. I'm really excited to be back in Blacksburg. I was born and raised 300 yards, 400 yards that way across from the airport, and went to Virginia Tech. So born and raised a Hokie, stayed a Hokie, and loved being back here with my family all still back here and all the childhood memories. But today, I kind of get to look into the future and think about, you know, what are the futures of my kids? What are the futures of my kids' kids and so on and so forth? And talk a little bit about the work and the companies that we're supporting at the Dominion Energy Innovation Center. So before I get too far into any presentation or any conversation, I have to put the disclosure in there that I am not the utility. We're actually a public-private partnership formed in 2009 between Dominion Energy, Hanover County, the town of Ashland, and then the Virginia Biotech Research Park Authority, or some of you might know them in Richmond as Activation Capital, to support Virginia's energy transition through that entrepreneurship and innovation lens. And our work centers now around focusing on the electrification of everything, right? And what is the utilities role in that transition? What is our industrial and our commercial and our residential load shifting or opportunity that we have to really get into as we look at the energy requirements of Virginia, the energy requirements of PJM, the energy requirements of the Eastern Interconnect, the nation, the world, right? And so we do this through a series of programs. We help entrepreneurs and innovators from that idea stage, still in a lab, all the way up to Series A, Series B, and exit through various programs, one-on-one mentorship, and then pilot-specific programs with Dominion Energy, which is the state's largest utility. It's also an investor-owned utility. APCO's the second largest, and then you have all your co-ops from there. But we'll kind of dive into some of that. So at Virginia Tech, I studied geography, so I am not an engineer. That'll preface any of this scientific discussion, but did take many a physics and chemistry class while studying geography. And so love the subject matter of energy because it's really how you look at what's happening around you in the world, what natural resources are we able to utilize, where do we place transmission lines, where do towns form, where do industries form, and all of that gives us kind of what we see and breathe and live around. So we offer mentoring, subject matter expertise, and then technical assistance as well. So with a number of the companies that go through our programs, we end up, depending on kind of the opportunity there and the look in Dominion's zone, end up serving as a technical expert as they look at securing stakeholder buy-in, financing, project build out and development. Verticals we serve, and this is just, I just have to level set on DEIC before we get into the fun stuff, so excuse the infomercial for 2 seconds. I'm trying to be my best Billy Mays here. But we work power generation to power delivery. So it's, if you have an idea that touches one of those, it can be software that manages vehicle to grid interconnection so that you can get paid for selling power back to the grid. When you're not charging your vehicle, say at that 4 to 8 o'clock range, when everyone gets home, turns their oven on, cranks their AC down, plugs their EV in. If you say work from home and haven't driven that much each day, use your car as an income maker, right? And so one of the companies that went through our Accelerate program in 22 now has a full-scale pilot rolled out with SEC approval, and they went through that whole process with us to get their vehicle to grid. It's a company called Weave Grid. We won't dive into too much to them today because I want to talk about that power gen side. So I work a lot with Dominion's business development team to focus on how are we going to meet the mandates of the Virginia Clean Economy Act? How are we actually going to produce the base load electricity that allows us to have our lights on, allows our hospitals to operate, allows our critical infrastructure to stay up and running, as well as how do we meet those peak demands. So as you can see, we kind of have a lot of verticals, and to date, our program, we're actually going to update these numbers because we just are kicking off tomorrow our fifth cohort of our Accelerate program. And these are companies that are at that Series A stage, ready to do a utility scale pilot with Dominion. And we take them through, this year will be an 11-week program to get them introduced to the business units, get them introduced to the stakeholders, build out that business case for the executives, and then get off to the races with a pilot within the DOM zone. But before I dive into the fuels, we kind of have to level set on what is a grid, what is energy, where are we all going in this, right? Because that's ultimately what we're trying to transition. Energy is not new, right? Society is defined by energy, and we have gone through a number of energy transitions over the life of our country, as well as over the life of human history, right? Starting with, of course, wood here in North America, or peat moss if you were in England, and wood transitioned into coal, transitioned into oil, to natural gas, and you start seeing in the 1950s and a little bit earlier the introduction of hydro. We learned how we could make really big dams, and those dams couldn't just power the water wheels that would power our analog machines that all had conveyor belts or had gears running them from that water. But we learned that we could electrify these, right? We could put generator on them. We could move current about. And then we started getting into nuclear, right? We learned how to split the atom. And then we use that power to actually create society instead of just destroying it, right? The Atoms for Good speech was the really pivotal moment when we realized that nuclear has to be a fuel source, right? Not just a war device. And we see a resurgence of that. We get very excited about the opportunity for nuclear across Virginia. We're one of the leading states in the Commonwealth for nuclear power. If you're unfamiliar with the Virginia Nuclear Energy Consortium or the Virginia Nuclear Energy Consortium Authority, because every authority, which is a quasi-legislative entity in the Commonwealth, also gets then a 501c operating arm under it. So we're the only state in the United States that maintains a strategic nuclear plan. And that's for our industry, that's for our power generation fleet. And of course, it's in relation to the DoD installations off of Norfolk and even in Lynchburg. So believe it or not, Lynchburg is the nation's nuclear hub when it comes to fuel assembly development, reactor development, primarily for the DoD, because we build all of the not submarines, anything but submarines that's powered by nuclear is built in Norfolk, and Powerboat up in Connecticut gets all the submarines. But we have quite the infrastructure and industry here, and we're always looking for ways to expand that. We have two facilities, North Anna and Surrey, which have 4 reactors between them. And Dominion Energy just a few weeks ago put out an RFP for a 3rd reactor at North Anna. That site has actually been licensed by the NRC previously when they were first developing that power station. And finally, we've gotten around to a point where there's opportunity to rebuild nuclear again, coming out of the human disasters in nuclear, coming out of some of that societal pressure that's been put on it. And I think there's a real understanding that there's no way to get to net zero without nuclear energy, right? It is the nation's current largest carbon-free power generation source. It provides that reliable base load, right? Which we typically rely on coal for. If you look at AEP, it's a 10 gigawatt coal company. That's a grid forming type of technology, right? Versus our grid following renewables, which we started to see the development really come out in the early 2000s. We really got a hold of the solar panel technology, the wind technology. We could finally put it into a form factor that would have some sort of economics behind it. Certainly there's been government incentive and government finances put into that to make that transition. But I think the most important thing here is to really think of energy transitions as taking decades and centuries, right? It's humans pushing the very bounds of what we're able to understand when it comes to powering devices, storing memories, and really running the institutions that make up our daily lives. And so human history ultimately is a function of energy, right? And there's never going to be a down trend in this, right? If this graph in any longitudinal way goes down below some of these bounding kind of peaks here, I think we're in real trouble, right? Because it shows that we're pulling We're pulling productivity out of a society, out of a country, out of a nation. And so there's always going to be this up and to the right. We just have to figure out how we power that cleanly, efficiently, in the space and form factor that we have. Yes, we are a country blessed with lots of land, but it's not infinite land. And so when we look at that actual land use and the land use discussions around solar and wind and geothermal and nuclear and coal and natural gas and hydrogen, and what are those form factors? How much land is required? What can we get out of that space, right? What's the highest and biggest use? And we see a shift of people wanting view sheds and people wanting agricultural land, and these competing forces of how we use our land. And so we just have to be cognizant in what natural resources. Natural gas made us, fracking ultimately made the United States fully energy independent. On a gross level, maybe not in the micro, in terms of what our refineries actually refine and what we can use versus what we need to export. But it put us on that energy independence. And we were there too with nuclear, right? Back in the 1970s and 1960s, when we had a workforce, much like China has the workforce now, that is able to build nuclear at 2-year intervals for $2,500 a kilowatt nameplate versus $10,000 a kilowatt nameplate in the United States, right? We have to really ask ourselves, why is it so much more expensive in the United States, and even to Europe, in some of the EU countries, to build nuclear versus what South Korea is able to do it at, what Russia is able to do it at, what China is able to do it at, right? And ultimately, at the end of the day, it's a workforce. We've forgotten a lot of how to build these big mega projects on time, on budget, and mainly through a skilled trades issue. It's the welders, it's the machinists, it's the kind of engineering hands-on tactility that goes into these large industrial systems. Which is the beauty of the IRA and the beauty of the bill and in our infrastructure funding that has come out, is we've put a whole set of folks back on the workforce. So we go from this idea of US energy to what are the specific systems and institutions within which our energy exists today. And we exist on what's considered the Eastern Interconnect, right? The Eastern grid. There's 3 grids in the United States. There's an Eastern grid, there's a Western grid, and there's Texas. Because Texas, everything bigger and better, except for some elements. And there is overlap, right? That everyone does talk about. There aren't those interconnection points. There is bleed, right? But it's not a significant amount of bleed to really help them when ERCOT gets into, say, a winter storm, or into what we just saw a couple of weeks ago with a massive heat wave, right? Where they were very close to blackouts across the state again, because of the load that was put on from all the chilling that was having to happen, right? Versus all the warming that had to happen. And that's the nature of energy. Is you need it in the winter, you need it in the summer, and you need it all year round, maybe just in different form factors. And so we exist in this Eastern Interconnect grid. And specifically, we exist in PJM. As you can see, there's the Pennsylvania and Jersey grid right there. In Maryland, PJM, Pennsylvania, Jersey, Maryland, that purple one is our grid. So, but PJM is itself a set of other sub-regions and categories, right? This is the geographer in me coming out. I live in maps. I love maps. This is what I live for, because this is ultimately where you think about, where do we run power lines? Where do we put power plants? How do we move energy, right? I think back to Game Changer Week last year, and I was staying with my parents out in Christiansburg, and Atmos or your natural gas company was doing work out there. And right in that Walmart parking lot, they had set up a mobile LNG interconnection while they took a 20-mile piece of pipe down. And there were about 17 LNG trucks sitting in this Walmart parking lot, regasifying, injecting into the pipeline downstream, right, while they took this other segment out. They needed to do work on I think it was a compressor station. But they were able to set up this entire thing. And so we think about the movement of energy, right? Is it's not just electrons, but it's also molecules. And so where are we moving those molecules? And in terms of electricity and utilities, what we think about a lot is those electrons, but those electrons come from somewhere. It's simply from burning something, right? We're burning uranium, we're burning natural gas, we're burning oil. we're burning wood, right? Or we're burning hydrogen and carbon. And so we live in this DOM zone and this AEP zone, right? And you know, it's really interesting. So you can see, I'll show you on the next map, you'll start seeing how these zones really start impacting us as consumers, residential consumers, right? You can see where APCO's territory is, right? Remember, right here, we have AEP's territory. AEP makes up a lot of this. APCO is just a fully owned subsidiary of American Electric Power Company. And so they have their zone in Virginia, and Dominion has its zone, but there's also a lot of co-ops, right? So there's actually a lot of utilities across Virginia that have some sort of say in where they get their power, what that power needs to be. But your two biggest ones are, of course, Dominion Energy and Appalachian Power Company. Dominion with just under 2 million customers in the state, and APCO with about 500 to 700, I believe. And they're the ones that are targeted by this Virginia Clean Economy Act 2020. We got legislation through that really pushed forward the advancement of renewables and clean energy, and the discussion and the legislation, and ultimately the systems, institutions, and opportunities that come out of that. And so we have an energy need, right? Back to the title of this section, I said one state, two systems. There's a really interesting story to be told in Virginia right now. That's a difference between what we're seeing in this part of the state and what we're seeing in this part of the state, right? That DOM zone versus that AEP zone. And more specifically, there's the APP zone within PJM. So it's a subzone of Appalachian or of American Electric Powers that's just looking at the Virginia instance of AEP. And so we can see that in the AEP zone, we are looking at a 10-year annual growth rate of about 1.4%. Now, if we actually dive into Appalachian Power Company's IRP, which is your integrated resource plan, and so every utility has to put out an IRP, and it looks out over 15 years and says, what are our energy needs going to be? How are we going to meet that, right? We have to have that balancing of load and supply, right? Our grid has to be balanced. And that's kind of one of those issues as we get into more and more penetration of renewables, is keeping that grid balanced. But APCO is saying in its territory, it's going to be looking at a 0.3% per year increase in industrial. It's going to be looking at a 0.3% decrease per year in residential. And on the whole, from 2033, you're actually looking at a negative energy growth rate, right? You're looking at negative 0.1% per year decline in the energy consumption in Southwest Virginia, right? Which is very different than looking at the DOM zone, right? And very different in understanding what actually is driving our energy consumption, right, in this day and age, right? I think it's very clear to see with the APCO statement quoted directly from their IRP that residential homes are getting a lot more energy efficient, right? There's components that are electrifying. We've electrified a lot of those components. There's not necessarily the electric vehicle adoption rate in Southwest Virginia as there is in Northern Virginia and the eastern part of the state, right? There's maybe not the population growth on the whole. And so you have energy efficiency, which is one way that APCO plans to meet the requirements of the VCEA by 2050. Dominion has to be net zero by 2045. APCO has to be net zero by 2050. And so they're trying to figure out where that how they get there. And that's what their IRPs. This day, you know, in this day and age, the IRP, and they're fascinating reads. Go look them up, Google them. They're great reads because they'll each lay out different plans, right? Here's plan A, here's plan B, here's plan C on how we're going to meet supply demand while also meeting the legislative requirements. And we'll actually dive into some of Dominion's. And so we have growth. We have significant growth in the DOM zone. And if we think about recent news, right? Data centers, right? Data center alley, data center hub, that's what Northern Virginia has. And it's trickling down 95, it's trickling out 66. And it's eventually going to, you know, and it is on its way down here. And so that's actually a huge opportunity, right? Everyone wants to talk about our grid constraints or our electricity problem, but at the end of the day, that's opportunity, right? That's growth, that's tax dollars, that's electricity generated, right? That's activity in these areas. And so whenever we're looking at these state regulations, we have to keep in mind there's kind of two competing elements going on here. You have one that has hypergrowth, you have one large territory that has possibly negative growth. And what are we doing to meet those needs, right? And is it just electricity versus natural gas, right? I mean, the proximity of Southwest Virginia to the facilities in full-on Appalachia and the Ohio Basin is phenomenal. And it's one of the reasons that the eastern part of the state really has to focus on electrification, is there isn't the infrastructure for natural gas. With the demise of the Atlantic Coast Pipeline, there was no way to get large quantities of natural gas to the coast. And so those businesses naturally, if they are to grow, have to grow on electricity because they can't afford to grow on natural gas unless someone would really want to take the financial investment to go get a Jones Act compliant LNG tanker and move from the Gulf Coast and move that energy up into Norfolk and Newport News, which there's been discussion of, right? But that's a large investment, considering some of the other Jones Act compliant vessels and import-export terminals. And so in that DOM zone specifically, we are looking at having to be net zero, fully 100% zero carbon generation by 2045. But think about that for a second. You cannot have a single carbon generating asset, or you have to buy a significant amount of renewable energy credits that could get produced from somewhere that are traceable for the lifetime of that credit and worthy of the kind of mission of the organization, right? You can kind of look up now all the scandal that there has been in forest or farming renewable energy credits, and how do you actually prove that that carbon's been sequestered, right? And so there's significant difficulty there. And so we have to figure out, there's already projected to be a gap there, right? Remember, we were going back to, 5.5% growth per year. And in some years, we're getting even up to 8% growth, 7% growth, right? And having to think about, how do we manage that amount of additional megawatts put onto the grid, right? So we're just squeaking by. In 2024, we were able to squeak by with maybe 2,000 megawatts of purchases from PJM, right? Keep in mind that PJM grid isn't just there as a regulatory body. That PJM grid is there so that we can buy electricity from anyone that's producing in that. So when you hear developers talk about their interconnection delays and all that, that's delays with PJM, because PJM ultimately manages and has to say in what generation gets placed where on their grid to actually move it around, right? And so that's what the PJM grid is. It's a collection of assets that allow you to generate and transmit, right? And then it's your utilities that ultimately have the distribution rights, right? And in Virginia, it's a monopolistic market. And so you have one utility, you have your muni, you have your IOU, you have your cooperative that you're buying electricity from. Well, we have two plans here. Back to that IRP, two plans, right? So we have a plan on the left that assumes no retirements. Dominion's vertically integrated in that they own generation assets, as does AEP and as does APCO. You own generation assets, you own certain transmission assets, you also own the distribution assets, right? So you can produce, you can move, you can then sell. And assuming that none of the plants come offline, right, in the DOM zone, or in Dominion specific, because the DOM zone isn't just Dominion, it's called the Dominion zone, but it has Rappahannock Electric, it has your Northern Virginia cooperatives in it, right? It has, and they're facing the same problems. The interesting thing with your cooperatives in Virginia is that they actually buy the bulk of their power from ODEC, which is the cooperative of cooperatives. It's the generation cooperative in Virginia. And so they own assets. They own part of North Anna Nuclear Station. They co-own certain biomass facilities with Dominion. They own other assets with other partners, right? But they generate for their 11 cooperatives that they then sell to throughout the state. And so in plan B, right? Assuming no retirements, Dominion's projecting a capacity gap of 16 gigawatts, right? 16 gigawatts, right? With retirement of their assets. So if they were to sell off or close, not just sell off, well, they could sell off, right? They could sell off or close their coal facilities, their natural gas facilities, right? Their biomass facilities. You're looking at a capacity gap of almost 28 gigawatts of generation, right? And as a consumer, you really don't dive into these. You kind of read on the surface what that means, but we all know economics, right? Vertical integration, you have efficiencies that come in, right? The scale, efficiency of scale. You can buy that firm load for your combined cycle. You can co-locate facilities. You can really invest in the infrastructure. When you ultimately sell off your assets and you are only capable of buying what the market will give you, right? Then you have an expense, a massive expense creep in. So you can just imagine the hit on a consumer bill. If all of a sudden you go from a utility that can buy cheap gas, right? Cheap coal, cheap uranium, right? To then having to buy that on the open market and expect it to be carbon free, right? Because it's not that they can just sell their assets and then buy whatever electricity. They still have to buy and deliver to Virginia consumers, as APCO is going to have to do, buy and deliver carbon-free electricity by 2045 or 2050. Right. And so if everyone in PJM is trying to do that, and everyone within the Eastern Interconnect is trying to do that, where's all that carbon-free electricity coming from? Everyone's going to be trying to do it, and it's all going to be driving up the market price. Who's going to be the generators, right? Are we looking at a future where generation is entirely separated from transmission and distribution? I don't know. You could, right? The utilities could determine that the more economic and easier route than trying to figure out how to do carbon capture, how to figure out how to produce hydrogen, how to get new nuclear built, how to build offshore wind, how to build onshore wind, how to do all these things is simply to get out of the generation game and leave the generation to private equity. And we all know what happens when private equity comes in, right? Like they typically love increasing the value of their assets and playing a bit of a fun buy and sell game, right? And that buy and sell is always making things more expensive because you have to find active value somehow. And so there's this real tension going on as we look out 5 years, 10 years, 15 years, 20 years to where is the electricity in this zone coming from, right? With 5.5% annual growth, with then the need for it to all be carbon free, and with the need for it to all be dispatchable on demand. We don't want rolling blackouts. We don't want blackouts. We don't want brownouts. We want to provide the electricity that consumers and businesses want when they want it on demand at an affordable rate. Wow, we get into some like real big, hairy questions. And so we've set up and worked with Dominion to look at the future. What's out there? How can we do this, right? What are the possibilities to solve these problems? And so I just kind of want to tell you how we're looking to solve some of those problems through the lens of 5 companies that have gone through or are going through our accelerator program, right? And specifically, I'm going to focus on the power generation and power transmission, because that's where our bottlenecks are, right? We're not so concerned about distribution. Distribution is relatively fine outside of the problems that we have getting transformers. But when we really think about that core nut that we have to crack, right? Almost 28 gigawatts or 17 gigawatts capacity gap in our territory, we have to really think about what that means. And in back to that societal context, where are these communities? If you've gone to Northern Virginia, you will see land is very scarce, land is very expensive, and you can't do too much to shrink a substation or shrink a transmission line or shrink a power plant, right? There has been, right? There's been incredible innovations around this. Dominion actually figured out how to put a number of substation elements subterranean and start stacking substation elements instead of expecting them to be drawn out wide, so you can put the same amount of power management into a smaller footprint, right? The market pressures of real estate prices in DC, where all the data centers are being built, is astronomical, right? And that's why you start seeing them creep down into Louisa, creep down into Caroline and Hanover County and into Culpeper, right? That's moving out to where there's just space, right? Data centers need space, power gen needs space, power movement and transmission needs space. So I want to start first with this idea of reconductoring, moving power, because I'm going to end on one specific use case that we're going to dive deep into as we talk and think about the circularity of things. So 2 companies, TS Conductor that went through our program 2 years ago, and Veer, which is going to be going through our program this year. These are 2 companies at the very cutting edge of what it means to have a bulk transmission system. Right, so look around you, all the big towers, right? Your 100, 120, 500, 750 kilovolt lines, those big ones, right? That look like they have arms, right? Are moving electrons over aluminum, right? So the bulk of our transmission system is aluminum conductored lines around what has historically been a steel core. You need the strength of the steel to give you the tension across your towers, but you need the aluminum for the conductivity. Would copper be better? Sure. Is copper ridiculously expensive? Absolutely, right? So you go with the next better thing, high purity aluminum, right? But there's opportunity there, right? Technology has come a long way. Wiring has come a long way. Our understanding of composite fibers have come a long way. And so TS Conductor set out in 2018 to bring to market a composite core with a new type of aluminum design encased around it to move up to 30 to 40% more electrons down the same right of way on your transmission lines. Right? Reconductoring is fundamentally about taking the infrastructure that you've already built, which is these towers in your right of ways, and put other lines down them that allow you to put more electrons down that same area. Right? It's pretty simple. We're going to upgrade the pipe, the kind of holding that we've already put there because we need to meet this electrification. And so our power lines right now are just braided, circular lines. But if you actually start looking at them in the trapezoidal plane and you wrap them around this composite fiber core, you can decrease your core size, right, while increasing the amount of aluminum around there. But because this composite fiber doesn't expand when it's hot. So our peak demand in Virginia is in the summertime, right? That's our winter peaks and summer peaks are not equivalent. We have a higher peak in the summer. And so if we can reduce that sag, right? Because as things heat up, as steel heats up, as aluminum heats up, it wants to expand. And so it sags on your towers, right? You can only allow but so much sag before you have to what's called downrate that line, right? So when that line is downrated at the peak time that you need power because everyone's plugged in their car and turned on their AC and is cooking dinner at night, right? When it's hottest during our summer months, you have to downrate your transmission lines because they're going to sag too much, they're going to arc, they're going to drop, right? And you're going to have some big problems. And so TS Conductor came up with a way of solving all of those problems, right? While still being able to put more power down the same right of way, right? So that's and it's more expensive, but it's not that much more expensive, right? And then on the far extreme of reconductoring is even thinking about what material are we even sending electrons down? What physics are actually constraining our ability to move electrons to their final destination? And so in this year's cohort, we're very excited to have Veer, which is developing a high temperature superconducting power line that's liquid nitrogen cooled online, right? So very incredible, right? We hear about superconductors when it comes to fusion and high temperature superconductors developed around our particle accelerators. Jefferson Lab has a lot of fundamental research in this. Virginia Tech, I'm sure, has way more knowledge in this than many of our other institutions. But if we can figure out how to put that into a form factor that doesn't require huge, facilities to chill, well, what started out at low temperature superconducting material, liquid helium, right? And we've moved up that scale quite rapidly to liquid nitrogen. And then we can harness that with the same physics, right? The same principles of moving power around our grid. We cannot increase our capacity by 30 or 40%, but we can increase our capacity online by 6x, right? And so in that same right of way, right, now with significant infrastructure updates, right, because you have to figure out how you cool this ribbon, right? It's not really a line, it's a ribbon, right? And if you want to check out a company, there's two companies in the United States, Furukawa up in New York and Medox down in Texas are producing this HTS, high temperature superconducting tape, right? And it's a tape. And one thing to highlight there is it's a tape that's built on top of a sapphire substrate within a lot of yttrium layers and a lot of really obscure metals that you've probably never heard of, right? But are fascinating when we think about these lines are actually semiconductors. They're not power lines. They're semiconductors that we're now stringing as our way of moving because now we have a resistance-free way of moving electrons to place, right? Which means that in the same form factor, we can fit a whole lot more power, which means we don't have to spend the 10, 15 years trying to get approved a new transmission line if that's ever going to happen. But we still have to figure out how we crack that nut on actually building generation, right? Because we still have to move all these things around, and we need to move these things around all the time. Data centers don't just want power when it's sunny out or when it's windy out, right? And there's not enough lithium or cobalt or magnesium and manganese and the 60 different critical elements that go into a battery to build enough utility scale battery storage where we wouldn't have destroyed entire countries by mining them to the core, right? And I think that's really the balance that we have to think about in all of this renewable energy discussion is, yes, we can build the wind and yes, we can build the solar, and we've built those for ridiculously cheap, but what are we doing with the power, right? Because fundamentally our power curves, right when your solar's peaking, right when your onshore wind is peaking, your power curves and your demand in across society is actually relatively low, right? It's one of your low points in our daily adjustments, right? Because people aren't at home, people are in their offices. There's a bit more energy efficiency here than at our homes, right? And so we have to store that power. So you hear people talking about, battery electric storage, right? So we're using big lithium ion batteries to store, or we're using lead acid or lead air or sodium or what, right? There's a lot of battery companies out there right now that are trying to build utility scale battery storage because there's no way for us to utilize solar power when it's not sunny unless we have it stored somewhere. And so Dominion Energy had at one point in time the world's largest energy storage system called the Bath County Pumped Hydro Station, which stored enough energy to power 700, which still does store enough energy to power 750,000 homes within a matter of 13-minute dispatch time, right? Because they have a reservoir at the top, they have a reservoir at the bottom, and they'll just open those floodgates and let the water down. China beat us out about 4 years ago, when they built the world's biggest pumped hydro storage facility, right? There was talk of doing another pumped hydro facility down in deep Southwest Virginia. I believe it was Tazewell, right? But that kind of has been waylaid. And so now we're kind of left with batteries. No one wants to fill valleys with water anymore because of the environmental impact. So if we're not going to store with water, we're going to have to store in some other medium. And so we can store in batteries, or we can store with hydrogen. And so that next kind of progressive fuel source, and I realized I should have put one more slide in here, back to that wood, to coal, to gas, the oil, right? That there's also a carbon chain complexity that we keep walking down in our energy transitions, right? We go from highly complex woody compounds, right? Think about the number of carbons, the number of hydrogens, the complexity of those organic chains. And we go down to what we have now, which is the bulk of CH4, right? It's a very simple molecule, right? One carbon, 4 hydrogens, right? And now we step down one further, right, into just hydrogen. Remove the carbon, right? We've put we've put an economic impact, a health impact on that one carbon molecule. And so now we step down that chain one more time and we say, what's just hydrogen, right? But how do we make just hydrogen? It doesn't want to exist, right? It's not an element that wants to be by itself. It gets rather lonely, right? And so we have to crack it from something. We have to break it from something. We can break it from methane, like C0 is doing with methane pyrolysis, right? We crack it when we burn it, right? That's where our furnaces burn carbon, right? Burn natural gas or burn coal is breaking those chains apart. And so C0 and methane pyrolysis is taking methane pyrolysis is combusting methane in the absence of oxygen. So you get solid carbon, not CO or CO2, and then you get hydrogen gas. So the carbon will fall out in their system. And there's lots of companies doing this. Monolith is another one doing pyrolysis. There's a lot of companies that are now doing pyrolysis from various things, trash pyrolysis, rubber, right? Different components, different oils. And so that's one option, right? C0, the interesting look there is they fluidize their reactor to the point where you can put that on the front end of a power plant. So you could still take your firm load that you've had to buy from Columbia or whoever your pipeline manager is, right? Your midstream pipeline company. And you can put a pyrolysis C0 plant on the front of that. You have one company that cracks your methane to provide you just hydrogen, right, into your power plant. Asset reutilization is a big component that a lot of people don't want to talk about, but we have all these gas turbines. We've got to burn something in them, right? Or we're just going to end up landfilling them. Fuel cells would be an option if they were more reliable, but you're rebuilding your fuel cell every 5 to 7 years, and that capital or that operating, that OpEx doesn't really net out when you look at the scale that you have to with these power plants. So you could crack your methane and still utilize natural gas, but landfill or uprate your pure carbon into graphene, graphite, carbon black for tires, whatever it may be, right? There's a whole chain of other products that you could, but you'll end up with a lot of carbon, right? Which is essentially coal ash is just carbon, right? With a bunch of other stuff in there. It's not clean at all. You have companies like Independent Hydrogen, which is doing really cool, innovative work capturing the chloroalkali flue gas, waste gas that comes off of our bleach plants. So bleach, right, is an intense process. I'm not fully baked on all the chemistry there, but it produces a lot of hydrogen in that process that they've since just been venting to the air along with the carbon dioxide. And so now there's a number of companies that are able to take that flue stream and actually just separate the hydrogen. They're not having to put any additional energy input to create the hydrogen. It's already there from the bleach production process. And so they're able to capture that. So you're taking an industrial waste stream and you're turning it into a valuable energy stream. And that, in many regards, that might be the future of how we get to our net zero, is this idea of waste to energy. There's chicken manure waste, right, that you can turn into ammonia with a company like Mova that I see sitting in the back. And there's other RNG from swine, from cattle, from landfills, from industrial municipal wastewater treatment plants. You can go down this whole RNG. At the end of the day, RNG is still burning methane though, right? We're still using combustion turbines, combined cycle turbines. The energy consumption there and the infrastructure for pipelines exists, right? But we have to figure it out. But then you have a company like GH Power, which is focusing on producing hydrogen through the cracking of water, much like electrolysis is. But instead of using electricity to crack the water, you use aluminum to crack the water. And this is a project that we've been working on for a little bit of about a year now. We got started with some of the folks working in the Hydrogen Tech Center that the CRC runs. But the idea being that aluminum is actually a pretty good energy storage mechanism. Aluminum, like hydrogen, does not exist in nature. There was no one picking up globules of aluminum, right, in the meso area, right, and or copper, right? They would pick up copper, they would pick up iron, or they would pick up these actual metals. But aluminum doesn't exist on its own. It exists as an oxide. And so through electrolysis, in large chemical baths and smelters, right? The United States only has 4 primary aluminum smelters anymore. We used to lead the world in it, but we no longer do because of how much electricity and how expensive that electricity is to produce. And so you look at countries that are producing large amounts of energy, right, that may have export constraints on some of that electricity or some of that energy. You can think about your oil-rich or gas-rich countries, right? A pathway could be to produce aluminum from electricity and then ship that around the world and then extract that, because there's no carbon in that aluminum when you actually react it with water. So if you take aluminum and you react it with water, if you get the right conditions, aluminum doesn't like to be by itself, right? Anytime you touch aluminum, you're actually touching a thin aluminum oxide layer on it, right? So that aluminum has oxidized, much like iron does when it rusts, but it doesn't look all that different. It's actually a beautiful white powder when you look at just pure aluminum oxide. And so you blow that off, and you expose the aluminum underneath of that oxide layer, and you hit it with water, you hit it with steam. It will then decompose into thermal energy, aluminum oxide, and hydrogen, right? And you can actually get very cost-effective hydrogen. And have similar, if you can get it in the form factor, aluminum makes for this idea of energy movement around the world, right? That's going to be one of those things that we really have to figure out, is where are we moving energy, right? There's talk of undersea cables to power lines to move energy. There's talk of other carriers, right? And then could aluminum be a new fuel? And so what does that look like, right? You can take recycled aluminum, you can take primary aluminum. If you have these reactors, and there's 2 companies that we've been tracking so far. One's GH Power, the other company is Found Energy out of Boston. This research of aluminum as a fuel source comes out of 2008, when NASA was looking at ways to cannibalize the rovers it would spin, or in spacecraft it would send out, And where would it be able to actually power itself and power society on the moon or Mars or anywhere else? So they were looking at this idea of self-cannibalizing robots that were able to eat their aluminum parts as they then kind of moved through space or landed and weren't needed anymore, right? And so take aluminum, put it into a reactor. Some can combust it, high temp, high pressure. Some can need a promoter or a catalyst to blow off that aluminum oxide layer to expose the raw aluminum. And in that, you are provided lots of exothermic heat, which you can turn into steam and drive industrial processes or drive a generator. You can also turn it into hydrogen, and then you have an aluminum derivative. These aluminum derivatives are used as the foundation of our aluminum transmission lines. We can turn it back into aluminum. So if you could take recycled aluminum that's alloyed, right? If we think about our cans as being an amalgam of different metals, there's probably 99 to 98% aluminum in there, but you have a lot of other things that they've been smelted down with. Because we take a big aluminum sheet, right? You put it into a big furnace, you melt it all down, you add that all together, and you get the lowest grade of aluminum to make our cans out of. But you also have primary aluminum, which is pure aluminum that then goes to secondary smelters to alloy into the right mixtures for aircraft engines, for bikes, for car frames, car engines, radiators, wheels, all of these things where we have a waste stream. We're again taking a waste stream and being able to upcycle it into energy in many regards, right? As well as upcycle it into the raw input to remake aluminum, so it can have a new life as pure primary aluminum, as our need for aluminum oxide increases, or we can take that aluminum oxide and we can put it into other industries. The battery separator, that barrier that goes in between your anode and cathode in your lithium ion batteries, is reinforced with high purity aluminum oxide to increase its strength, so you don't have migration of the materials and you don't have essentially these dendrites that form and break that barrier, causing your battery to short out and you lose that cell in your car. So you're increasing battery safety, you're increasing battery longevity. Or you take aluminum oxide and sapphire. If everyone knows the sapphire gem, well, that's nature's way of dealing with aluminum, right? And aluminum oxide, it produces sapphire. And so now there's companies that take high purity aluminum oxide and produce synthetic sapphire, which makes up the base of every LED light, LED screen that you've seen. It makes up the base of all of the microelectronics that go into space because of its density and its and it is a very low electrical conductivity ratio. And so it doesn't allow radiation to mess with your microchips, right? That sapphire is also the base, as I was saying, of these high temperature superconducting ribbons that could be the movement of our electrons into the future, along with everything on top of it, right? So we could start thinking about the future of our clean energy, of our energy transition, may not be as simple as all solar and all wind, but it could be a combination of a lot of these. And we have to get really creative with how we actually think about where we find these fuel sources, where we find this energy, and then what that actually means for us as an economy and as a market to actually spur these, innovate these, and move these technologies to market. So I think I'm getting the hook here from Laura, but I really appreciate everyone's time. I'm going to be on a panel at 12 o'clock today, and love to talk to you after this or see you there. But thank you all for the time and opportunity to be here.
That's great, and he's just amazing, like his expertise. And if you want to ask questions, because we didn't have a lot of time, please feel free to mingle with him downstairs, but he also is going to be here for the lunch and learn. That'll be here at noon, and there'll be more time to talk and ask questions then. So please stay for that. And that's free too. But I also want to make sure that you guys know that there's a bunch of other things happening this week. We have the showcase tomorrow with free headshots. We have the halftime reception tomorrow night at Eastern Divide. Just look at the Hooba app and find the things that you can attend. We have free co-working space downstairs. So if you need to pop in and out and do some emails, feel free to do that. But we really appreciate you guys coming. And thank you so much. We have an incredible speaker next. Bill Diamond from E1 Air will be here talking. So if you want to stay for that, please stay. Otherwise, take a little bit of a break. The restrooms are right over here and we have snacks downstairs. We look forward to seeing you guys. Thank you. Thank you, Braden.
Hey, how are you? What organization? Economic film.